there's lots of information on structure and bonding, and it goes from quite simple at the start to quite complex at the end. So at the very start, we just have solid, liquid, and gas, and we need to know effectively the defining point. So for a solid, we have our atoms or particles are in a fixed position. They just vibrate. They cannot move, and the material itself cannot be compressed. When we compare that to a liquid also cannot be compressed. That's because there is little to no space in between them. In reality, it can be compressed slightly, but it's pretty much negligible. So we say they cannot be compressed. But these particles can move around each other. If they can move around each other, they can float, and it fills the shape of the container. Whereas the solid had its own shape, and it keeps that shape. A liquid does not, because the particles can float. When we go to a gas, the particles can still float. They still move around. But this time there's large gaps in between them, so they can be compressed. So when we're trying to differentiate them, we say that these two, solids and liquids, cannot be compressed. The gas can be compressed. Your solid cannot float, it holds its own shape, whereas the liquid and gas does float. So we've got some definitive things that we can say about solid, liquid and gas. And these are the particle diagrams. So even though you've been doing these for a very, very long time, they are particle diagrams. So when it says about particle diagrams, it's these. We need to know about the phase change or the state changes. The easiest ones that most people know is we've got solid to liquid is melting, and reverse we've got freezing, then we've got boiling and evaporation, and then we've got condensation from the gas to liquid. We also have sublimation. So sublimation is quite unusual, so the solid goes straight to a gas. And we also have deposition, which is a gas to a solid, but I don't think we need to know that. Then we go on to what actually happens to the particles. So it's very, very similar. So if we have a solid, the particles vibrate. If we just apply energy to those particles, as they heat up, the particles will vibrate more and more and more. At some point, the particles will start to move around. At that point, the particles get further away, and the temperature will actually stay the same as you give energy, but instead of vibrating more, the particles can then start to separate. As the particles start to separate, the particles can then flow. If they can flow, it now becomes a liquid. That's very, very similar to the reverse freezing. So the particles can flow over each other and move. As they cool down, they get slower and slower. And at a certain point, the particles can no longer move over each other. And at that point, it's frozen into a solid. If we go back to melting, if we were continually applying energy to these particles, they will keep moving and moving and moving, faster and faster. And if we applied enough energy, the particles would have enough energy kind of leave the bulk substance, and at that point would be boiling or evaporating. So we can use a heating curve or a cooling curve, and what will happen is at this point we've got a heating curve, so the solid is together. As we heat up our solid, the particles vibrate more and more. This is why the temperature increases. At a certain point we'll be putting the energy in. That energy no longer makes the particles vibrate more, it makes them move further apart. And as they move further apart, that is melting. So as it melts, we do not get a temperature change because the particles aren't moving any faster, they're separating. And then once they've all separated, they can then start to move faster and faster as they're a liquid. We can use this to check one of the fixed points. So we've got the melting point is a fixed point, your boiling point is also a fixed point, and we can use these to identify chemicals, and we can use them to identify if your chemical is pure or not. So this would be pure because it's a nice flat line. If it was more curved, or if it was staggered, it would show that it's just an impure substance. So we've also got something really basic that we need to know for this unit. If we take one particle, it does not have the properties of the material. So if we were to take nanoparticles of gold, so we've got very, very small particles, not necessarily one particle, but very, very small. They are soluble in water, and they have like bluey pink colours. If we were to look at the bulk substance of gold, it is definitely insoluble, and it's nice shiny yellow. So one particle, or very small particles, do not have the same property as kind of the bulk material. So one limit to the particle model is that the particles are all spheres. Molecules are very, very rarely spheres. If anything, the only one particle that's going to be a sphere is going to be your helium. All the others, they're not going to be spheres. And we always draw them as spheres. So that is kind of one limit. Another limit is that the particles will interact with each other. Even helium, which is extremely inert, doesn't interact with nearly anything, will interact with each other when they're in a gas. So these particles do interact with each other. So even if they're not charged, they will interact. Even if they're inert, they will interact. And the particle model doesn't show this. So the particle model, even though it is useful, does have its limitations. Alright, next we go on to compounds. So compounds are when we have two or more different types of atom that are chemically bonded. If they're not chemically bonded, they are a mixture. But if they are chemically bonded, they are a compound. So we've got three different types of bonding that we need to know. We've got ionic bonding, which occurs between a metal and a non-metal. Your non-metal will be a negative ion, your metal will be a positive ion. We have covalent bonding, which is a shared pair of electrons between non-metals. And we have metallic bonding, which is between two metal atoms. So initially we're going to look at ionic bonding. So the first thing we need to do is turn our atoms into ions. So an atom is always neutral. So on the periodic table they are all atoms, they have the same number of protons and electrons. But we don't want that, we want ions. When we're making ions, what we would do is we need to turn the electronic structure of the atom into one of a noble gas. So if we have sodium, sodium's electronic structure is 2A to 1, so it has one electron in the outer shell. We could either add 7 electrons, which would turn into argon, which would be very difficult, or we could just remove one and effectively turn it into neon, or neon's electronic structure, which would be very easy. So your sodium will lose 1 electron and become 2,8. And overall it has a positive charge of 1. Your chlorine is 287 normally. So what we could do is we could either lose 7 electrons, which is extremely difficult, or we could gain 1 electron, which is considerably easier. So it would turn to 288, which is the electronic structure of argon. Overall it has a negative charge of 1. So when we're drawing the electronic structures of ions, we put them in square brackets and we'll have the charge at the top. So if we were making ionic structures, if we were doing the dot and cross diagrams, so these are the dot and cross diagrams of ionic compounds. And you'll always have the ions, the square brackets, and the charges on. These charges will need to cancel each other out. So with my magnesium, we've got 2 plus, and we've got my oxygen is 2 minus. So they cancel each other out. If this was chlorine instead of oxygen, chlorine would be -1. So we would need 2 chlorines, and we would simply put a 2 in front of the chloride, and we put 2 in front of the chloride, and that would be able to cancel the charge on the magnesium. This magnesium oxide will have if we go back to sodium chloride, so if we put these next to each other, it would be sodium chloride. The charge difference is 2. We've got +1 and -1, so the charge difference is 2. If you go to the next one, we've got magnesium oxide, the charge difference is 4. And that means it has a greater electrostatic force. And it's the electrostatic force that holds ionic compounds together. It's a very, very strong force. And this strong force means it has a high melting and boiling point. And the difference between the charges affects the actual melting point and boiling point. So a bigger difference means a stronger force. A stronger force means more energy is needed to overcome it. More energy to overcome, which means a higher melting boiling point. So you could predict that magnesium oxide has a higher melting point than the sodium chloride because of that electrostatic force. So it's really important that we say that these are giant ionic structures. They are not molecules. You do not get a molecule of sodium chloride. You do not get a molecule of magnesium oxide. A molecule implies a small, discrete unit. When we say NaCl or MgO, they are ratios of the ions to each other. So a sodium chloride structure will have trillions upon trillions of ions within it. It won't just be one sodium and one chloride. So our structure, NaCl, is simply a ratio. Because this size structure, or the NaCl, doesn't have a fixed number of NaCl, it just has a fixed ratio. So we do not call them molecules, we call them structures, or giant ionic lattices. So when we're producing ionic structures, or ionic compounds, these are the ions that we need to know. You've got group 1 makes +1, group 2 makes +2, group 3 makes +3. Group 4 doesn't really make ions. Sometimes they can make negative ions and sometimes positive ions, but ultimately they're not going to make ions. Especially at our level, they're not going to make ions. Group 5 will be -3, group 6 will be -2, and group 7 will be -1. So these are the ones that you can kind of work out from the periodic table. These are the ones we need to remember. So we've got a sulfate ion, is SO4 2-, and we've got a nitrate ion, which is NO3-, a hydroxide ion, which is OH-, and a proton, which is just a hydrogen ion of H+. I wrote proton because you can actually get an H-. We call it a hydride, but it's out of our specification. So that's why I called it a proton and not a hydrogen ion. So we need to be able to work out the formula of salts. It is relatively simple. So if we have sodium bromide, if we go look up sodium on the periodic table, we know, is it going to do it? So we know it's Na, then it's 1+, because it's in group 1. Then if we go look up bromide, it's in group 7, so it's going to be Br1-. So you wouldn't normally write the numbers, but I have just to make it easier. Then all I'm going to do is I'm going to move this 1 to in front of the bromine, and this number in front of the sodium. So I would have Na1, Br1, but just like in mathematics, you want to have 1. So the formula for sodium bromide is NaBr. If we were going to do cesium chloride, so I'd go look up cesium, so that's Cs, and it is in group 1 again? Right, we won't do cesium then, we'll do a more difficult one. We'll do calcium. So pretend that says calcium. So we've got Ca. Ca is 2+, because it's in group 2. Chloride, again, group 7, so it's -1. So we've got +2 and -1. All we do is we move the numbers over again. So we've got Ca1, Cl2. So we get rid of the 1 again. So we've got CaCl2. When we're making these salts, when you're making these ionic structures or this ionic formula, all you're really doing is you're trying to cancel out the charges. So this had +1, this had -1, so 1 of each. The calcium had +2, so it would need 2 -1s to get rid of it. So when we've got giant ionic structures, we've got several ways to represent it. We've got the 3D model and the ball and stick model. The 3D model is quite good because it shows you the minuses are bigger than the positives, so a positive ion is always going to be smaller than the negative ion. And it shows you that the electrostatic forces come in many, many directions. These electrostatic forces, which are really strong, they will be in nearly every direction. this doesn't show you realistically how far it is from the protons to each other. So it's not to scale. If we were to look at the ball and stick model, it's better in some ways because it shows more of a distance between the nucleuses, which is more correct. But again, it's not to scale. And these might even be smaller than they should be. So we're not to scale, but it does show you a good visual representation. So this one shows you the bonds or the electrostatic forces. This one normally doesn't show you it, but both of them can be used, but they do have limits in their models. And again, this is a giant ionic lattice. Right, so your giant ionic structures, they are held together by these strong electrostatic forces. They are normally in 3 dimensions because if you've got a positive ion, you can have a negative one above it, below it, left, right, back, forwards, everywhere. So you have lots of these strong electrostatic forces. And these strong electrostatic forces, they need a lot of energy to overcome, so it's a high melting and boiling point. So if we're thinking about more properties, so one that we need to know is that if we have a solid ionic structure, the particles, they are charged, but they are not free to move. Because these charged particles are not free to move, they are in a fixed position, they cannot conduct electricity. What we need to conduct electricity is we need our particles to be free to move. So what we could do is we could dissolve them in water, make a solution, or we could melt them. Once your ionic substance is dissolved, so once it's aqueous or once it's molten liquid, we have charged particles that can move. If we have a charge that is moving, we have an electrical current. So by dissolving our ionic structure, or by melting it, it will conduct electricity. If it's solid, it will not, because the particles cannot move. So whenever we have conduction, we need a charged particle, and we need it to be free to move. So when it's solid, it's not free to move, but when it's molten or aqueous, it is free to move, so it can conduct. So in summary, we've got giant ionic structures are called lattices. They're held together by electrostatic forces. These electrostatic forces are very strong, so they require large amounts of energy to overcome. And that large amount of energy is through a high temperature. When solid, they do not conduct, they insulate. And when they are dissolved, when they're molten, they will conduct. So we must remember those. So next we're going to covalent bonding. Co means to share, and valent means the outside electrons. So we've got some non-metals there. When we're doing covalent bonding, we are not doing ions, we are doing effectively the atoms. When you are drawing molecules for covalent bonding, you don't need to draw the inside electrons, so we could quite simply just use the group number. So chlorine group 7, so we could use 7 in the outer shell. Carbon is 4, so we could draw 4. Oxygen 6, so we could draw 6. So what we can do is, if we're thinking of chlorine has 7 electrons in its outer shell. It wants 8. So what chlorine can do is it can share 1 electron and it will receive 1 back. If it shares 1 and gets 1 back, it would effectively get 1 more electron, so it would be 8 in its outer shell. It would have the electronic configuration of argon, and it would be stable. So here's my 2 chlorines together. This chlorine has shared 1 electron, this chlorine has shared another electron, and by sharing electrons, they both have 8 in the outer shell, so they're both stable. If we have a shared pair of electrons, this is a covalent bond. So this is a single covalent bond. If we shared 4 electrons, it would be a double bond, so it would be 2 covalent bonds. If we shared 6 electrons, it would be a triple bond. So every time we share 2 electrons, 1 from each atom, it's 1 covalent bond. And co means to share, valent means outside electrons. and 2 electrons makes 1 bond. 1 electron comes from each atom. So there's my lovely drawing. So if we were going to draw this, if we wanted to draw HCl, we would draw our H, or our electronic structure of hydrogen, our electronic structure of chlorine. We can see that the hydrogen wants 1 more electron to get the electronic structure of helium, and the chlorine again wants 1 more electron. So what they can do is they can overlap. So if this was a Venn diagram, the hydrogen can now see 2 electrons, so it's happy because it's got its outer shell complete. The chlorine has 8 electrons, so it is happy. And if we just check, the hydrogen had 1 electron there, and the chlorine had 7 electrons, we've still got 7. So we've not created or destroyed any electrons, but both of them now have the electronic structure of a stable noble gas. So they're very happy. So simple molecules are very, very small. So, well, they're relatively small. They might be maybe 100 atoms, but they are simple. We can normally identify these as they're normally a gas or a liquid at room temperature. Again, we have these models. They're not to scale, and each one has its advantage. So we've got a 3D model, shows the true bond angle. We've got a 2D one, even though it's quicker and easier to draw, might be easier to kind of read, but it doesn't show you the true bond angles. On some of them, we've got electrons, so these two show electrons, but they don't show bond angles. And then ultimately, we've got ones that are very quick and easy to read. So even though each model has benefits, they all have their drawbacks as well. And we could pretty much always say, when we're drawing models of atoms, that they're not to scale. Because drawing atoms to scale would be absolutely ridiculous. We don't have enough space on a pencil or on a paper to kind of draw the size of these atoms compared to the dots that we can draw for the nucleuses. So these models are never to scale. So these are held together by weak intermolecular forces. When we are melting or boiling a simple molecule, we do not need to overcome or break the bonds, just the intermolecular forces. Inter means between, molecular, in between the molecules. So we have forces holding the molecules together. These are very, very weak. So that's why at room temperature, these simple molecules are normally a gas. Sometimes they're a liquid, sometimes they're a solid, but they are usually a gas. Because these forces are very, very weak. So they do not require much energy. And that not much energy is normally a low temperature. So the bigger the molecule, the bigger the intermolecular forces. It's purely because there's more electrons. So it's easiest to represent, so to look at hydrocarbons. If you've got a relatively large hydrocarbon, so this is probably going to be a liquid. If we take a small hydrocarbon, it's going to be a gas, purely because there's less intermolecular forces here, and there's more intermolecular forces here. Or this is a stronger intermolecular force, this is weaker. If we were to take carbons with maybe hydrocarbon with 40 or 50 carbons, we'd be talking a solid. We also need to think about what the atoms are. So if we take fluorine, fluorine is a very, very small atom with very few electrons. It has 9 electrons. If we compare that to iodine, iodine is significantly larger and has 53 in each atom. So I2 will have 160 electrons. F2 will have 18 electrons. Because the iodine is significantly bigger, because it has more electrons, it has a stronger intermolecular force. So that's why iodine is a solid at room temperature and fluorine is a gas. So it's not just amount of atoms, it's what the atom is as well. So that's why we can presume acetine will have an even higher melting point than iodine, because it has even more electrons, it's a bigger molecule. So bigger molecule, stronger intermolecular forces. So these covalent molecules, these simple molecules, even though they're free to move, they do not have a charge, so they do not conduct electricity. So chlorine, iodine, bromine, oxygen, nitrogen, they do not conduct electricity because they're not charged. like giant covalent structures. So giant covalent structures are not simple molecules. So you cannot call giant covalent structures molecules. These again are massive structures where we say simply a ratio. So our oxygen, simple molecules, gas. Our silicon dioxide, even though it's made of very similar stuff, it is a giant structure. It has completely different properties. So your simple covalent had a really low melting point and boiling point. Your giant covalent will have a very, very high melting and boiling point. So how you would determine if it's a simple or giant covalent structure is its melting and boiling point. So these giant covalent structures are held together by very strong covalent bonds. Whereas before, in simple, we were being held together by intermolecular forces and we had to overcome those. In our giant covalent, we have to break covalent bonds. So it requires a huge amount of energy. So to break them, to change their shape, to scratch them, we have to break bonds. Instead of just intermolecular forces, we're now breaking bonds. And that requires a huge amount of energy. This time we've got no charged particles, we've got no movement of particles, so they do not conduct electricity. And none of them are soluble in water. Your sand is not going to dissolve in the ocean. We have some exceptions. So carbon can take many forms, they're called allotropes, and one of them is graphite. So graphite, we have our normal covalent bonds. So each carbon has 3 covalent bonds. If you want to break those, you need to put in huge amounts of energy because you're breaking bonds. But we actually have a 4th electron on each carbon that is free, is delocalized. And that electron can move between the layers. It can move backwards and forwards. And that electron is negatively charged. So because we have a free 4th electron that is negatively charged, we've got a charged particle that is moving. So your graphite can actually conduct electricity. Unlike basically any other giant covalent structure, which are insulators, graphite is actually a conductor. And it's got that 4th electron that is free to move. That electron can also carry thermal energy. The graphite will conduct thermal energy as well. So where graphite is different to diamond, the bonds in between the layers are extremely weak because they're not covalent bonds. So the layers will slip over each other. So it requires very little force to make the layers move. So this is how your pencil works. As you drag your pencil across, you're leaving layers of graphite on your paper because there's no covalent bond holding them together. They also can be used as a solid lubricant, purely because the layers will slide over each other very, very easily, which again is very unusual for a covalent material. And it's purely because that 4th electron isn't covalently bonded. So we've also got 2 more structures that we need to know about. We've got fullerenes and we've got graphene. So our fullerenes they started off with C60, and when it was discovered it was like a series of pentagons and hexagons put together like a ball, and because they looked similar to structures by an architect called Buckminster Fullerene, they were called Buckminster Fullerenes. So they're named after an architect. We can also create nanotubes. Nanotubes are like graphene or graphite, but they're into a tube shape. They have very high tensile strength, so they could potentially be used for things like wires or cables. They can conduct electricity and thermal energy, so it's very unusual. So these things are currently not used, but it's kind of a technology that's never arrived. We're constantly looking at things to use, or we're constantly looking at new methods that could potentially use these, but we haven't found them yet. At the moment, they're useless, but we might one day in the future find a use for them. So one that's far more interesting, that's far more promising, is graphene. So graphene is a single layer of graphite, and what can happen is, because it's very thin, and it can still has that fourth electron that can move, it can conduct, but it's extremely light. So if we were to replace metals, metals are generally very, very dense. If we can replace metals in things like microchips and phones, or in satellites, we can get them to be considerably lighter. The lighter they are, they're obviously, if it's a satellite, it's going to be easier to get into space, or you can put more things into something a smaller place if it's going to be lighter. And ultimately this is what's helped us produce flexible displays.